All right, so now let's move on to our final topic and our most important, which is Shannon's theorem. Shannon's theorem gives the capacity of a system in the presence of noise. Now, Hartley did a nice job of giving us a physical reality of what if we have a limited resolution in our receiver, but really didn't talk about noise. And you can sort of think about if my signal comes in and is noisy, then my receiver may mistakenly receive one of the signals because the noise plus the signal may go over one of its threshold. So the resolution of the receiver was one constraint, and then the noise is the other constraint. And what Shannon looked at was using probability, can we figure out a relationship between noise and the final capacity of the system? And this was the equation that he proposed. And it says that the capacity of a channel is B times log 2 of 1 plus SNR. Now, a couple things I want to point out. The first is this is B, it's not 2B. So while it looks like Hartley's and Nyquist's equation, it is different. And the second aspect is that this is SNR, which is the signal to noise ratio, which is a power ratio. And we can write SNR simply as the signal power divided by the noise power. And what I've shown you here is the equation of this in dB. So I should point out this is the linear SNR, and this is SNR in dB. And what you should see is I can give you SNR in dB, or I can just give you SNR in linear terms. Both are the same, but mathematically we'd have to treat them differently when we're doing equations. And I just want to point out that the signal power and noise power are related to the square of the voltages of the actual signals. And when we talk about noise, we can only talk about RMS noise. And of course, for a signal, we could also talk about the RMS of the signal that's there. But we're always talking about the RMS noise, RMS value of our noise. And just make a note here, you need to check that your given SNR is stated in either dB or linear, right? Because Shannon's equation has it in linear. And so you'll get mixed up if your problem gives it to you in dB and you forget that Shannon's theorem has it in terms of linear ratio. All right, so let's use this and look at some examples. Let's assume we have a noisy channel with an SNR of 0. What's the capacity? So C equals B log 2 of 1 plus 0. So what's log 2 of 1? This is just simply equal to 0, and so the capacity is 0. Makes perfect sense. If my signal to noise ratio is 0, then basically I have no signal power compared to my noise. Now let's look at a noiseless channel where SNR is infinity. And so C is equal to B log 2 of 1 plus infinity. And this is just going to give us infinity. And so our capacity is infinite. And so the question is, how could we have an infinite capacity? Well, we've seen this before. We just have to choose M. If we let M go to infinity, that means we don't have any constraints in the real world. We theoretically could get an infinite capacity. So let's go to something a little bit more real world. Let's look at a telephone line, and it has a bandwidth of roughly 3 kilohertz, and an SNR we assume is going to be greater than 30 dB. What is the maximum bit rate or capacity of the line? Okay, so C is going to be equal to 3 kilohertz. That's the bandwidth, log 2 of 1 plus 30, right? Nope. Made a mistake, right? We don't put in the dB. We've got to put in what this is in linear scale. And 30 dB equals 1,000. So this is 1,000. So I end up with 3 kilohertz times log 2 of 1001. If you calculate this, this is roughly 9.97. And so we end up with our final channel capacity, calculating that out, is 3,000 times 9.97 equals 29.9 kilobits per second. Okay? So you can see how we can calculate our maximum channel. Now I should point out in specifically with regard to telephone, Just because Shannon's theorem tells you that's the maximum capacity doesn't mean that is what you are going to receive. It just means it's the maximum. In fact, you'll often get a lot less because Shannon's theorem is based upon probabilities and also includes the idea that you can put in error correction to overcome some of the mistakes that your receiver gets. So Shannon's theory isn't what you get without any fixes. Shannon's theory tells you what you'd get if you tried all of the possible ways to do error correction. So without error correction, we're not going to get anywhere close to Shannon's capacity. And once again, just remember to convert dB to linear so that you don't run into any problems. So let's look at a quick case study. I think this is interesting because it really highlights how people have progressed with respect to spectral efficiency and noise in Shannon's theorem. So in the 1980s, modems started with a 300 baud, 300 bits per second using a two-state frequency shift key. They then moved up to a phase shift key. They moved up to more levels, 4 to 6 levels phase shift key. And then finally, they went up to 9.6 kilobits using 16 QAM. And because they were able to reduce the noise on the telephone line, they actually were able to get up to a rate of 2.4 symbols per second. Now, I remember I mentioned before that the bandwidth was roughly 3 kilohertz. And you see here they're transmitting just at the bandwidth. They should be able to go twice as fast, right? Well, because the channel was so noisy, they couldn't transmit any faster. And so this is what they were limited at for a long time. And then some breakthroughs came in the 1990s where they introduced error correction. And as I mentioned, error correction gets you closer to the limit. And so there was 19.3 kilobits and then finally 28.8 kilobits. And this involved error correction. They were able to increase the symbol rates to 3.2 kilosymbols per second. And they went all the way up to 10. So I'm just going to calculate real quick to make sure I know what I'm talking here. But 2 to the 10 is 1024 QAM. Okay? So that's a pretty high number of symbols. And so you might ask, why didn't they go faster? Why not, go to 40 kilobits, 80 kilobits? And really it has to do with these two fundamental limitations. One is bandwidth. They don't have any more than around 3 kilohertz on a phone line. And the signal-to-noise ratio doesn't get much better than 30 dB. Now, there are some approximations you can make for higher SNR. And it allows you to make quick calculations of Shannon's theorem like you might do for a quiz. First off, we can approximate 1 plus SNR as SNR itself. And now what we're going to do is note that log 2 of SNR is really just solving for n. We want to know what the number is, 2 that gives us the value of SNR. So really we're trying to solve for this n. And so what I'm going to do is take the log of both sides of this equation, so 10 log 10. And you can already see what I'm trying to do. I'm trying to get this in terms of dB. And we just do a little bit more math. The n comes down. And the log 10 of 2 is 0.3. And 0.3 times 10 is going to give us 3. So 3n equals SNR times dB. And so n equals the SNR divided by 3. And what you need to remember is that what we're solving for is log 2 of 1 plus SNR in linear. And what this tells us is basically this whole thing is basically equal to SNR in dB over 3, where remember n is the answer to what this equation would be. And so we can write Shannon now as C equals B times SNR in dB over 3. And you can see that's really simple to use. So let's go back to this example. We can solve this really quick. C is equal to 3 kilohertz times 30 dB over 3 dB equals 30 kilohertz. So you see it works really well. So let's look at what the effective M of Shannon's theory would be. Because remember, Shannon's theory is not talking about levels. It's dealing in an abstract idea of signal and noise. But maybe we want to try to get some physical feeling for what that means in terms of levels. And so what you can do is just equate the two to try to figure out what this M would be. If you go through and solve this, you end up with M as being equal to the square root of 1 plus the signal-noise ratio. Remember, this is in power. And so we take the square root to get everything in terms of voltage. And you end up with M is roughly basically the peak voltage of the signal divided by the peak RMS voltage of the noise. And this is very reminiscent to the Hartley of A, our peak amplitude, over delta V. And so let's tie it all together. We get a channel bandwidth of 1 megahertz and 54 dB of SNR. Find the maximum bit rate. Well, this is pretty easy, right? We just take C is equal to 1 megahertz times 54 over 3. That equals 18. So this is 18 megabits per second, right? Now let's find the number of symbol levels. And if remember, we've got 18 megabits per second. And now we're going to go back to the Hartley formula, or Nyquist formula of 2b log 2 of m. So this is going to be 18 megabits per second over a bandwidth of 2 megahertz, right? Because we multiply by 2. And that equals log 2 of m. This right here is just 9. And so m equals 2 to the 9th, which is 512. And let's say we had an RMS noise of 2 millivolts RMS. What must the signal be in RMS? And remember, all we're going to say is that the V signal over the V noise is equal to M. And so we just take 512 times 2 millivolts equals 1,024 millivolts, or approximately 1 volt is what our RMS of our signal would be if we had 2 millivolts of RMS noise in order to even attempt to get this. Now this is just giving us a rough feeling for where the bounding areas are for this, because remember, this equation that we're using here is an approximation. It's not actual derivation, but it's more of a good feeling for what we would need. We would likely need more than this in order to get the resolution we need, but it gives us a rough idea.